This program is brought to you by Stanford University. Please visit us at stanford.edu.
I have the results of the part of the problem set where you tried to verify the correctness of the scaling argument for walking. And this is when you were on all fours. And apparently there are some genetic problems here and there. Maybe only 3 limbs were touching the ground at a time. It's not clear what's happening here. But generally, you can see that we fall on the curve. So that little analysis works. Unfortunately, if you blow it up to include the entire data set, that's of everybody in the class, there's some real unfortunate ones. This person apparently, Max said, disappeared into a hole and then came crawling out somewhere else. There's some others over here that are pretty, that should reconsider their major. But this is troubling, and this was while running. And I'd suggest that we're not going to actually divulge identities. It was not a camel. That we suggest you seek therapy. And on 2 legs, I presume this wasn't on 2 arms, but on 2 legs, actually, interesting enough, the spread is greater. And I think maybe it's because when you're on all 4, you're a little bit more constrained. But again, we had some issues here on the lower end of the curve. We had, looks like this other person inverted himself or herself, came up here. Little problem here. But generally, most of you, passed the test of humanity. And you can see the power in that analysis. It really does work. So today we're going to start a new unit, if you will, or a new discussion, which will continue for this lecture and 2 more. So that'd be 3, and this is on issues of the fate of contaminants in the environment. Many chemical engineers end up in the job market, if you will, or in a career where they deal either retrospectively or prospectively with problems of the environment. And by that I mean either trying to design processes which are inherently green and clean before you turn them on, so you don't cause environmental damage, or trying to disentangle environmental damage that has occurred due to either poor design or abuse or poor operation of a process or a plant. And this will probably be an interesting career area as we go forward for many, many years to come. Now, why is that? Well, certainly up until about the 1960s, I would say, maybe the late 1950s, we, meaning society and all around the world, treated the planet as if it had the capacity to infinitely absorb all waste materials in any way, shape, or form, whether you threw them on the ground, buried them, tossed them in waterways, lakes, rivers, the oceans, or into the air, into the atmosphere. And the Earth, which had a population of something in excess of 1 billion people at the turn of the century, and now we have over 6 billion, appears to have finally reached its limit to absorb or take in the wastes at the rate at which they're being produced. And we've had some harbingers of issues in the past. As a kid growing up in Los Angeles, it was common for us to go out in our backyard where we had a hole, maybe 6 by 6 feet by 4 feet deep, and you would throw everything in this hole. You'd throw your trash, your garbage, everything. And once a week, you'd light it on fire. And it was the beginning of primitive incineration. Now, it turns out incineration does quite a bit to reduce volume of waste. And in fact, incineration is a process that's been used in societies certainly since the Middle Ages and probably before. In the Middle Ages, as the toward 800s, 900s, that era, they had wagons called fireboxes, which were lined with clay. And people would drag these down the roads through villages, and people would toss their waste in as it went by, and it was on fire. And it would just be on fire all the time, and it would be dragged back and forth, and people would just dispose of it. It was kind of a moving fire pit. Now, one of the things that happened in Los Angeles, of course, is that being surrounded on 3 sides by mountains and with onshore breezes which would tend to compress and collect atmospheric pollutants, something called smog happened. And part of smog, which is smoke and fog combined, which it really wasn't, it was generally photochemical materials that were reacting in the presence of sunlight to produce a very sort of brown material interacting with ozone. And it was harsh to breathe, and your eyes would tear. And I remember going months and months without seeing the mountains behind my house, which were only 2 blocks away. So regulations were formulated, rules, statutes, laws, to prevent such things as outdoor burning of waste, controlling point source emissions from various segments of industry and so forth. And slowly but surely, the air became cleaner. And actually, it's in fairly good shape today, but not without having made a lot of statutory effort. The other issue in Los Angeles, of course, is automobiles. And when I was a kid, you would use leaded gasoline. And the reason lead was put into gasoline was to prevent knocking in the engine, which is sort of a form of detonation on the piston heads that give rise to a pinging sound. And tetraethyl lead, as it was called, had the ability to even out the flame front and get rid of knocking. But of course, you would exhaust lead, which turned out to be bad. And then lead was taken out of paints. And then you'll probably remember the ozone hole. So atmospheric scientists noticed this hole in the ozone opening up over the Antarctic and closing and opening. And that was related to the scavenging halogens that came from chlorofluorohydrocarbons, which were used in spray cans as propellants and were used widely in refrigeration systems, both in automobiles and in homes and in industry. And those have been banned. And they were banned actually by treaty for use around the world. And so other materials had to be found to be used as refrigerants, and they were. And in fact, Stanford has gone back to ammonia, compressed ammonia, to chill the water. I don't know if you know, there's a chilled water loop on campus, which that chilled water goes into essentially the radiators over which air blows to provide a means of air conditioning on buildings on campus that are air conditioned. And this cold water comes from the fact that at night all these air conditioners for the most part are turned off, and compressed ammonia is used to make a giant ice cube. And out under Forsyth Hall is an enormous underground vault in which an enormous ice cube is made every night. And then this water loop starts up in the morning and flows over the top of this ice cube. Heat exchanges by melting the ice, lowering the temperature of the water, and that's pumped around the campus. And of course, the game is it never gets hot enough, they hope, to melt the entire ice cube before people turn off their air conditioners. And it's now happening on a fairly regular basis, particularly in hot weather, where this giant ice cube melts before the end of the day. So if you go out on Robley Field, you'll see a green fence. Behind the green fence, you'll see a bunch of chillers, which are the auxiliary chillers that are now used to pick up that peak when, on hot days like last week, the ice cube melts sooner than you would otherwise want it to melt. So it's a form of heat exchange. You guys know all about that. Yeah. It's about the size of maybe 70, 80, 100 feet by 100 feet and 10 feet thick.
If you use that system, there's no pollutants that come out, or compared to when you would use it?
Right. So as long as the ammonia stays in a closed system, because it's being compressed and then evaporated and compressed to absorb the heat from the water to make the ice, then the answer is no. If there was an ammonia leak, that would be bad. But if you have to put ammonia in the atmosphere versus chlorinated hydrocarbons, I think you'd choose ammonia. You just wouldn't want to be nearby. It'd be like a big, bad smelling salts. And it'd be very unpleasant. You would leave. So the other areas where there have been environmental disasters, and it turns out that this very week I'm working on one. So actually this is a good time to be lecturing on this because it's uppermost in my mind. You would expect industry, or I would have expected industry, and I testify to this on occasion in litigation, as to the appropriateness of how engineers designed systems back in the 1960s and occasionally 1970s, that is chemical processes. The case I'm working on right now is against Dow Chemical Company. So let's see what you think. So here's the situation. Dow Chemical Company, which began in Midland, Michigan in the late 1800s, a guy named Herbert Dow, was a business built on making chlorine by electrolyzing brine, which is salt water. So you take sodium chloride, you put it into an electrolysis cell, it splits sodium from chlorine. Chlorine gas is evolved. You make hydrogen, and then the hydroxyl ion latches onto the sodium and you make caustic or sodium hydroxide. So the business was made some hydrogen, made some chlorine, and made caustic. And he made a business. Dow made a business selling that material. And the chlorine, it turns out, would be used to make hydrochloric acid. So people who needed base or acids, you could get it this way. The company evolved into finding out if you take this chlorine and you put it onto hydrocarbons, you can make chemicals that have interesting properties. Some might be, if you start with methane and chlorinate it, you'll get chloroform, you'll get methyl chloride, methylene chloride, and carbon tetrachloride. If you take ethylene and chlorinate it, you'll get a 1,2-dichloroethylene, or you can get 1,2-dichloroethane. You can then strip a chlorine off of it, and you can make something called vinyl chloride. And vinyl chloride is the precursor to polyvinyl chloride. Huge, huge market for PVC. And Dow eventually went into that business. And so they would make just about every chlorinated hydrocarbon in the book, including chlorobenzene, They would make propylene glycol through a chlorination process. And in the end, they became a very, very, if not the largest, at least the second largest chemical company in the world. Now, when you make these materials, they don't come out pure. You get byproducts. And the byproducts can be pretty nasty. They're highly chlorinated, called heavy ends or bottoms, things like hexachlorobenzene, hexachlorobutadiene, hexachloroethane, dibenzo P-dioxin, furans, and you've probably heard about dioxin. So really nasty things. You need to get rid of these things. They just they don't have any worth. They don't have any value. And it was typical that chemical companies would simply hawk this stuff into the nearest river, the Great Lakes, throw it out on the ground. And you sort of have to wonder, what were they thinking? But it was sort of the commonplace way of doing business. And in the, would have been the late well, actually, in the 1930s, some companies like Dow began incinerating their waste, putting them in incinerators and burning them and trying to get them down to essentially CO or CO2 in water. And of course, you'd evolve, if you're burning a chlorinated hydrocarbon, you'd evolve chlorine gas, and if there was water around, you'd make HCl, and if you didn't have, essentially a refractory lined material, if you had any metal around, it would eventually corrode. So this was a problem, particularly at high temperatures. So whether it was Dow or DuPont or other chemical companies, they typically would go out and scoop holes in the ground and just dump this stuff in the holes. Now, you might ask yourself, what do you think happens next? So what do you think happens if you dump this stuff in an unlined pit in the ground? It does what? Leaches into the soil.
Gets
and then
into drinking water.
And then what's under the soil, or in the soil? Aquifers, water. So then you get a problem of contaminating what it is you're drinking, and it all starts to go south from there. And it was until people started finding contamination in their aquifers that they complained to their legislators, congressmen, city council, whatever, and laws began to be passed about not only what you can emit or discharge, but where and how much. And so out of that came RCRA, the Resource Recovery and Conservation Act, CERCLA, the Conservation Environment, Reclamation Liability Act, SARA, all in the 1970s and 1980s. And you did a problem set on Superfund, which is from CERCLA. And what that was is, if one of these sites is found, many times they're found and there's nobody around anymore because they've taken off. And the government will step in and attempt to clean it up. And as part of that, they will attempt to find out who dumped there and when, and then go out and sue them and try to get the money to pay for the government having to clean up this mess. And I've been involved in several Superfund litigations as a result of that. So what I'm going to do is talk to you a little bit about what happens when these kinds of chemicals are put on the ground. And this is really nothing new. I mean, certainly the chemists and the chemical engineers back in the 60s, when I was in your shoes, going to school at Berkeley, knew about these things. But it's unfortunate that industry didn't take the lead or the initiative. And you might say, well, why, in terms of advanced incineration processes or destruction processes of these materials. And of course, generally they'll hide behind, well, nobody else was doing it. Or if we did it, we wouldn't be competitive. That sort of thing. And so that's why we have rules and regulations. In a sense, that's why we have stop signs. If everyone just agreed to stop, you wouldn't need a stop sign telling you to stop, right? I mean, we can't. Have you ever been I was driving around the other day and the street lights were out? man, it was like a three-ring circus. I mean, there were cars piled up on every street corner, and everyone's just running through and hoping, you know, just, oh man, look at that, no light, cross your fingers and gun it. And, you know, it's like driving in Brooklyn. So let's talk about a little bit about the environment and how it works and what happens to chemicals when they're dumped into the environment. So the hydrogeologic cycle is really driven by, this is not the moon, the sun, which of course evaporates water from the land, clouds form, it rains, and you guys aren't drinking your beer again today, are you?
It's coming, the sun is below the troposphere.
Well, you know, this is a metaphor sun. It doesn't really mean to be there. It used to be up here, but in that overhead, it's kind of drained down. So it's now here looking at this cloud, which is raining. And you have some snow, perhaps, and you get runoff. Everything goes downhill to the ocean. If you get depressions, you can form lakes. If the groundwater table, and what this is basically a line where the ground below this is saturated in water. So you have to think of water as ground as being a porous material. It has space in it, voids. They can fill with water. If they're full of water, the place between saturation and unsaturation is called the groundwater table line. And when it intersects the surface, you generally find surface water, whether it's a lake or a swamp, a river, or a spring. And water flows downhill, so if there's any gradient to this, the water will actually move through the ground, albeit slowly, sometimes only a foot or two a day, but it moves. And then you may find that you have highly consolidated soils like clay, silty, which is a very low permeability, and can effectively act as a barrier to the transport of water, and so you end up with these little underground rivers, if you will, or it may be on top of bedrock. And in fact, Lake Log is a good example of, that's a fake lake, and of course Lake Lagunita makes no sense because it translates into Lake Little Lake, but it's what we call it. And when Stanford built that as a watering hole for his horses, he didn't line it with anything. He just depended on sort of the silty soils that we have around here to contain the water, which it does, but it does leak like a sieve, which is why they have to dump water from the lakes above Lake Lagunita, Felt Lake in particular, down to get any water into that lake at all, because it drains out pretty fast. It's an unlined structure. So the sun drives all this, and there's a lot of water moving in places that you don't see it. You see the rivers and you see the lakes and streams and springs, but in fact you only see just a very, very small fraction of the water that is in and on the surface of the earth. So this water, when it lands on soil, can infiltrate the soil. We've always known this. Sometimes it can actually find places where the soil is consolidated enough that it doesn't pass through it, and you can get what's called perched water. You can actually get a very highly saturated area. You can finally get down to the saturated water. So this is a saturated area above the water table, or the capillary fringe as it's called. And then down here you have fully saturated material, and in this case it shows it moving from left to right. And it's into these confined or contained aquifers that we stick drills in and screen them. So you make a hole, you put a casing around it to keep it from falling in, and at the bottom you put it literally a screen, like a window screen, through which you pump the water. And the screen is such that it keeps out most of the dirt and the sediment around it, so that you're not just pumping dirt and water up at the same time. And that's how wells work. And you create a negative pressure by putting a pump at the top. Between what?
Saturated and unsaturated.
Okay, so if I have a sponge, and the sponge is, I set it out in the sun and it dries out, and I hand it to you, that's unsaturated. It's not holding any water. If I stick it in a sink and I squish it up and I fill all those little pores of water and hand it to you, that's saturated. So you can think of soil in the same way. Now, if I only put it in the water for a real short period of time and give it to you, I might not have filled all the holes. That's unsaturated. Not totally unsaturated, but it's not considered saturated. So you have various degrees of partial saturation before you become 100%. So 100% saturation, all the pores are filled. Okay? And then, as I said, the pores are all interconnected. So that's why the water can flow. So you have to think of it like a tortuous network through which the water is going down by gravity from high points to low points. So as I said, you stick holes in the ground. You can complain about the sun again on this one. And so the problem is we humans have done things like, if we want to get rid of noxious materials, we might dig a small shallow hole and just dump the material into it. This is called lagooning. That gives it a kind of a nice touch, like the Blue Lagoon, those two people running around naked. You didn't do that here because all your skin would be eaten off if you jumped into one of these things. You'd be a little skeleton running around after a while. And what happens is, of course, if you don't make the bottom of this and the sides of it impermeable somehow, like lining it, material will leak down, seep through into the ground, and get into this fresh aquifer and potentially contaminate it, particularly if this is your house and here's your faucet, and this just pulls this over and brings it right back up again. This is how you can get contamination in wells. Or you can have a big landfill dump or refuse pile, same thing. It rains on it, soaks it. It can remove contaminants, take them down into the water table. Now, another clever thing people did for many years is they would actually put very deep wells in the ground called deep injection wells. And they'd actually inject the waste and pump it into the ground. Now, what on earth they thought where it was going? I guess the idea, if it's deep, you get it below where these people are pumping. But see this little arrow here? And so there's a little arrow here, and there's the little people drinking. So this is the direction of the groundwater movement. Pumping wells can actually change the direction in which groundwater flows. You can imagine like sucking a Jamba Juice. It sucks it to the bottom of the straw. You can have so-called septic tanks or cesspools. Those are nice little things too. Well, that's just another hole in the ground in which you dump human waste. And it's typically sort of out of sight, out of mind, not in my backyard kind of thinking. And for a long, long time, the aquifers were sufficiently large and had sufficiently enough recharge that they could sort of naturally dilute this material. But then comes, around turn of the century into World War I, and particularly into World War II, I noticed that these chlorinated hydrocarbons, like perchloroethylene, which is tetrachloroethylene, and that's used in dry cleaning establishments, and trichloroethylene. I don't know, you probably know the chemical. So that's vinyl chloride with the hydrogens here. And if I put and then there's dichloroethylene, here's trichloroethylene with a hydrogen here. If I replace this with the chlorine, I get tetrachloroethylene or perchloroethylene carbon, and that's used in dry cleaning. Well, trichloroethylene turns out to have very, very good oil solubilizing characteristics. And so if you have metal that you want to paint, You have to get the grease off the metal. Otherwise, the paint won't stick. So for painting aircraft, painting metal Venetian blinds, metal parts of any kind, they would take these metal parts and dip them in vats of trichloroethylene, which were heated, such that the trichloroethylene vapors were coming off, and you'd actually set the part like this in the vapors. You wouldn't actually put it in the liquid. The vapors would come up and condense on the surface, and then the oily material would be dissolved. It would drop back down into the tank. Eventually, you'd keep cranking up the temperature of the tank because the vapor pressure of the trichloroethylene would begin dropping as you begin putting oil into it. And then finally, you'd have to heat it so much it was no use anymore. So they would take these tanks, which held maybe 55 gallons, and they'd dump them into a 55-gallon drum. And then they'd put it on a dolly, and they'd wheel it out the back door, and they'd just dump it out on the ground. Which, when you ask people why they did that, they say, oh, well, because it all evaporated. Well, that's bad enough. I mean, you're putting this in the atmosphere. But maybe they think the atmosphere is so big, no one would ever notice. But in fact, what happens is these chlorinated hydrocarbons have specific gravities in excess of 1. The specific gravity of tetrachloroethylene is 1.6. So when you go out and throw it on the ground, and there's water on the ground, and water saturating the pores of the soil, what do you think the tetrachloroethylene does? It sinks. It sinks like a rock right through the water. Now, why? One, because it's heavier than water, and number two, it's only very, very slightly soluble in water. It's like oil and vinegar in a dressing. Now, it's not zero solubility, and this is the real kicker. It's slightly soluble. So what happens when you dump a chlorinated hydrocarbon on the soil? It sinks, and then when it finally gets down to where the groundwater is flowing, it gets carried along with it. And this is called a contamination plume. And this is why you can have a spill here and a well 5 or 6 miles away, and you get contamination because you're intercepting this underground river. Another thing that can happen is it can sink down, and all the way, in this case, this is a dissolved contaminant plume, which is something that's more soluble than the chlorinated hydrocarbons. For the chlorinated hydrocarbons, which are much less soluble, they not only sink, but they go down and they sit here on a relatively impermeable material, such as clay, and then they equilibrate with the water passing by due to their low solubility. So they typically don't get transported, but they sit there in a puddle, equilibrating. Now, it takes a long time for these things to equilibrate. But now the next question you ask is, well, what's the drinking water standard for trichloroethylene? It's 5 parts per billion. In other words, if you have water that has more than 5 parts per billion of trichloroethylene in it, you shouldn't be drinking it, because that's exceeding the safe water drinking standard. So what does 5 parts per billion mean? It means 5 gallons of trichloroethylene will contaminate 1 billion gallons of water to the minimal drinking water standard. Well, that's a lot of water that flows by here, 1 billion gallons for every 5 gallons that gets dissolved into it. And this spill may contain several hundreds of gallons. And so now we're talking about many, many billions of gallons of water that get contaminated by this. And now you say, well, let's remediate it. Let's cure the problem. Imagine you're sitting here on the ground, and you're trying to figure out where this puddle is. You can't see it. You can't detect it. It could be 50, 60, 100, 150 feet under the ground. And you can drill all the holes you want, and you'd probably miss it. And there's no way of actually finding, these things are called DNAPLs, dense non-aqueous liquid phases. So then what they do is they go down here and they drill a whole bunch of wells and they start pumping as fast as they can this water that's flowing by it. But now you've taken this pure phase, dissolved it at 5 parts per billion, and now you're pumping all that water up and you got to clean it. Can you imagine how much water you've got to clean? Billions of gallons of water before you can return it back into the soil again. So these have to be massive cleaning facilities, extraordinarily expensive and energy intensive.
If you can't find that puddle, like, isn't it unnecessary to clean the water anyway because you're contaminating it?
If you can't find it? Well, if I could find it, I could suck it out in principle, right? But since I can't find it, and I know it's going to equilibrate, I want to intercept this contaminated water that's coming down because it's just going to go down and keep contaminating everything below it. We call these interceptor wells. So imagine you've got a river coming at you that's all contaminated. The idea is that you would suck that river up, clean it, and then put it back in. Your other choice is just let it go, right? And let it contaminate everything wherever it gets all the way to the ocean. Or maybe, I've worked on cases where this material is actually going down ancient creek beds under the ground, heading toward a major aquifer that services maybe 1 million people, or 2 million people, or 3 million people. You have to stop these things. The only possibility is luck. If you know where the stuff was spilled, if you know something about the hydrogeology, you might have a chance of actually sticking a wellhead into it. But these puddles, to hold several hundred gallons, they could only be, 3 feet by 5 feet. And boy, you talk about a needle in a haystack. And the cost of drilling a well, it's huge, particularly if these things are down several hundred feet. So this is a real problem. And unfortunately, in our country, we have many, many such places. For instance, Hewlett-Packard, right here on Page Mill Road, has recovery units in it in the parking lots. They kind of cover them up so they don't look like recovery units. You maybe have seen gas stations that have closed down, and there's fences around them, and you'll see a bunch of equipment. Well, those are basically pumps pumping stuff up, trying to get out the gasoline that's leaked out. Now, typically, gasoline's a little easier because what does it do? It floats. So that doesn't mean it doesn't dissolve in the water to some extent and contaminate water, but at least you have sometimes a better chance of getting at it. I worked on one case, which I'll tell you about, but just to give you an idea of the enormity, this was a dump, a waste dump. I calculated it would take 500 years for it to clean itself in a natural sense. All those 500 years, it's contaminating groundwater downstream. Nature was not prepared for chlorinated hydrocarbons. They had never existed in nature before. They're called anthropomorphic compounds. They've been made by man, by humans. And there are no, for instance, organisms that would naturally eat them as a means of digesting them and using them for energy. There are now some that have evolved because we've put so much in the ground. These bugs are sitting there, whoa, maybe I ought to sort of, change a couple base pairs here and see if I can eat that crap. And they do. It's called co-metabolism, and they can digest it. The problem is they generally need another hydrocarbon substrate to get cranked up. And so actually to clean up at Moffett Field down here where the big hangars are, the old blimp hangars, they actually pump toluene into the ground to feed these organisms so they'll not only eat the toluene, but they'll get cranked up. It's like getting on a big toluene high, and then they go eat the bad stuff. And a lot of people have a lot of trouble with the notion that I'm pumping something like toluene into the ground to clean up tetrachloroethylene. But the organisms, they work really very slowly. It's not something that's easy to implement. So one of the things I'll do in the next couple of lectures is show you how you can, as an engineer, make estimates of how much of these materials would be emitted from a facility. And I'll focus on ponds or lagoons or liquids as opposed to emissions from soil, for instance, which is just another kind of problem, which is also doable. And so you need to have kind of a model to start with, because we need a model. And once we have a model, we can apply mass balances and our rate equations to the problem. And what I'm setting you up for is about 15 years ago, I was asked to calculate, as part of a litigation, the release of volatile organic hydrocarbons. So this would be things like tetrachloroethylene, perchloroethylene, chloroform, methylene chloride, and other bits of the periodic table, out of ponds that were used from 1955 to 1971 at a place in Southern California, where people would bring tanker trucks and dump the contents of the tanker trucks into these ponds and then go away. And this was a certified Class 1 hazardous waste site in the state of California. It had been certified by a young geologist who graduated from Berkeley, who went down there and he looked at this canyon and he said, oh, it's all granite. It's like a porcelain bathtub. Dump all you want. It's not going to go anywhere. They paid him $300. He made this analysis by sitting on a rock, munching on a bag lunch, and then he took off. Turns out, yeah, it is all granite. It's all highly fractured granite. And so it had all these hairline cracks in it through which this stuff would ultimately seep. Over a period of 17 years, they dumped 37 million gallons of waste materials in these pits, these leaking pits. And my job was two things, of course, happened. Some of the stuff evaporated, and some of it went into the water. So it was an air pollution problem, and it was a water pollution problem. And there was a town downstream of this site, in this canyon, called Glen Avon, blue-collar place. Lots of stories had come about, one lady said Muffy, her dog, came in after a rainstorm, playing in the gutters. Turns out the site had overflowed. Muffy came in, ran around in circles, its eyes were bulging, finally his eyes popped out of its head, things like that. Chickens were born with no beaks. What if you're a chicken, you have no beak, how do you eat? You just go pound your head against the ground, and hope it goes in the hole. I mean, it's nasty. They had animals born with more feet in some cases and less feet in others. And, it looked like something was going on genetically in this town. And so animals that reproduce more rapidly than we do show these genetic defects sooner. And so my job was to calculate how much stuff escaped into the air, because that's the only way you can then feed that into a meteorologic model, which says if the winds are blowing at such and such a speed and such a direction, how much actually got down to the town. Then the people are the receptors, so how much did the people get over time? Then you hand that off to the epidemiologist who says, if you got that much for that period of time, it will cause this kind of adverse health consequence and make you ill. And then those people would beg for recompense and for remuneration for the losses that they've incurred. Now, these health kinds of losses are really tough to prove in court because we don't have a lot of epidemiology for people that have been breathing low levels of volatile organic hydrocarbons for long periods of time. What we do have epidemiology for is people who breathe high levels for short periods of time, like in the workplace. You open a bucket and you stick your head in and take a deep breath. That's bad. And so there is epidemiology for that. But certainly these people lost their property values. No one wanted to live there. Their property values went in the tank. And so there were about 4,500 people that I helped to represent. So what I'll do next time is I'll show you how we take a little model of here's a pond right here, and here's the air up here, and we have to figure out if you have a concentration in the liquid phase of some material like trichloroethylene, what will be its concentration in the gas phase above that pond? And I'll show you how I made that calculation, tell you a little bit about the trial. And this will take us about 2 lectures. So next lecture, I'll set up the analysis and the math for you. And then on the next lecture, I'll tell you how I used it and testified in the courtroom, hopefully to convince you that being a chemical engineer is a very cool thing to be. You can save the world too.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.